In the next 3 videos, we're going to motivate the loss function we'll use for logistic regression. And in this first video, we'll show you why squared loss is not going to work well for logistic regression. All right, so we left off with at least a model. And now we would like to choose a loss function so that we can fit the model and find our best value of the parameters given the data. When we were doing this in the context of regression, we were using either squared loss or absolute loss. And in fact, we used squared loss for ordinary least squares and had great success with it. So, will this still work? Let's see what happens. Pitfalls of squared loss. All right, we are going to play with this toy data set. And so I just have a small number of X values here, and they're mapped to either 0 or 1. And so this is what I would like to fit. And because I have a very simple model, I only have one input, X. Let's actually assume no intercept. So really my model is just of this form, right? And I would like to find the best theta for this data. So really, if I'm using squared loss, then the mean squared error is what I'm going to try to minimize. And that actually looks like this if we go plot it. Let's go over to the notebook to see this. So we are still in the logistic regression notebook, and you're going to scroll down to choosing a loss function. That's where we're starting here. And just make sure you have ran all the cells above. Okay, so first thing is we can actually, let's actually start on this toy data set and we'll come back to our tumor question in just a minute. So here's the toy data set. And when I go to plot it, this is the same plot that we had on the slides. And so now I'm interested in plotting the loss surface. So again, I'm defining the mean squared error just like we have in the past. My model is of this form. So this is my mean squared error function. And when I plot that as a function of theta here, what I want you to notice is this function that we're going to try to minimize is going to cause some problems for our numerical optimization algorithms, right? Ideally, we'd want it to find this theta, and sometimes it will. But the problem is, depending on where that numerical optimizer starts, it might get stuck up here because basically it stops whenever it gets to what seems to be a flat area, right? Like the bottom of a valley here has a slope of what's called 0, right? And so it's going to stop where it gets to a slope of 0, but that means it might get stuck there, or it might get stuck here or here. And so we'll see that in this example where I'm going to try to minimize it. Oops, let me zoom back in. And there's a name for this when you have this issue with the surface. It's called not convex. And we'll talk about that in the slides in just a minute. But usually if you don't have a convex loss function, it causes problems in trying to make sure you actually get the correct minimum theta value. So notice here, or the minimum loss, right, and the right theta. If I randomly, I'm using the scipy.optimize.minimize, that's just a built-in numerical minimizer here. It says that my best theta is 0.54. Okay, that looks pretty good, right? That looks like that's probably right. And I'm going to plot it now. And that looks great in terms of like, oh yeah, it actually seems like a pretty good fit. Okay, so you're thinking, well, what's the problem? Well, if I had run that with a different starting point, because notice I have to give it a starting point, an x sub 0 there. So now if I started instead at -5 and I run this, well, now it's telling me that the best theta is -10, which I know is not true. And when I go plot the fit with that theta being -10, I mean, that looks horrible, right? That's not a good S-curve for my data. And so part of the issue that comes in with using squared loss is the fact that I won't necessarily always get the right minimum. But there's a couple other issues. So let's pop back to the slides to discuss these. So we saw in the notebook that one of the issues was we may not always find the correct minimum. And the mathematical way to describe this problem is actually because the mean squared error function is non-convex. And one way to visualize that, you can either think of it in terms of second derivatives from calculus. You need the second derivative to be greater than 0 for all theta, so it needs to be concave up, which is not here. Or you could also just draw a secant line, and that secant line always needs to be above the function here, and I can see it's crossing the function. So I don't have convexity, and so that means I'm going to have an issue with my numerical solver trying to find the minimum, and that's what we saw. This will also be an issue even if I add more predictors. This is the one that we saw in the notebook again, where I can get wildly different incorrect answers. Now, even if I add another predictor, so here's adding on a intercept as well as a theta 1, I still get this non-convex cost or mean squared error function where, again, ideally I'm going to end up in the actual minimum, but it's quite possible that my optimizer will stop as soon as it gets to a flat area and give me the wrong parameter values. The second main pitfall is, if you notice, the biggest value you're ever going to get for this difference in here is 1, because this is a number that's either 0 or 1, and this is a probability between 0 and 1. So I'm squaring values that are less than or equal to 1 and taking their average. So at the end of the day, this is just looking at the squared loss for 1 point. The worst it's ever going to be is 1. And that's problematic in the sense that if I'm way off, with one of my predictions, I don't really have a way of reflecting that in this loss function, because at most I'm going to say, well, it was 1. It would be great if we could really penalize big mistakes more than just always being capped at 1. And the last pitfall of squared loss is, from a conceptual standpoint, it's a little tricky because we basically have class labels here of 0 and 1 that we're trying to match to probabilities. We're taking the difference and then squaring them. And it begs the question, maybe we should be matching class with class and or probabilities with probabilities, but not necessarily trying to combine them and do this in this form. So in general, mean squared error and classification is usually not used. I would say it's occasionally used in some neural network applications, but overall you're going to avoid it. So we need a different loss function. And we'll look at this in the next video.